Assalamualaikum and welcome back. We are going to learn bonding of organic ligands to metals. Before this, we have learned one type of one type of ligand, which is carbonyl ligand. So we do know how these carbonyl complexes are formed. So today, we are going to learn another type of ligand, which is called olefin. So olefin is a compound consists of carbon-carbon double bond. So it is also known as alkene or ethylene. So I'm pretty sure that everyone knows this. So we call this ethene as pi donor ligand. So because it can donate electrons from the field pi orbitals of the ligand to the metal. So before this, we define ligand as the compounds which have at least a lone pair of electrons. Only then it is having the ability to donate those electrons to the metal. But if you look at this Lewis dot structure of your ethene, there is no lone pair exists. You see, all electrons are being fairly shared with carbons as well as with hydrogen. As opposed, you can see for carbonyl, carbon from group 14, oxygen from group 16, two electrons shared, a pair of electrons shared from each atom. So we still have 1, 2, 3 electron pairs or lone pairs. So these electrons are normally used to be donated to your metal. But can we still consider olefin as a ligand, even though without the presence of lone pair? The answer is yes, we can. Why? Because the definition of ligand can also be extended to any species that are electron rich, like ethene molecule. Why it is electron rich? Because your ethene has this double bond. When it has double bond, it's gonna have definitely pi electrons. So those pi electrons are said to be rich. Okay, so since it is having rich of electrons in this area, it can donate these pi electrons to the metal. So those who are donating the electrons or electron donors are said to be Lewis acid, Lewis base, and those who are receiving the electrons are called Lewis acid. Now, olefins can be said to be an ideal pi donor ligand. But remember, when your ligand donates the electrons, there is a possibility for the electrons to be donated back to the ligand. So if this happens, then your ligand, your olefin also can be said to be a good pi acid ligand, which they can accept electrons from the metal. So what do we understand here? Number one, without the presence of lone pair, olefin still can be considered as a ligand. How? By donating pi electrons to your metal. Your ligand in this case is Lewis base and your metal is a Lewis acid. Now moving on, the first organometallic compound synthesized is an olefin complex. So it is known as this salt. I'm sure we have seen this salt before this. It was synthesized in 1827. Now this is the chemical formula for your zest salt. We do not know the structure not until it is revealed by the X-ray crystal structure. So from this structure, we can see that K plus is located outside. Inside this, we have platinum with three chloro, and we have one olefin ligand. So ethylene or ethane was shown to be coordinated approximately perpendicular to trichloroplatinate, and the hydrogen is seemed to be bending away from the metal. So this is how all the atoms in zest salt are coordinated. So the bonding in this compound has similarities to other pi acceptor ligands. See? So pi acceptor ligands like ones that we did before. So in order to understand the mechanism for the formation of ethene complex better, we need to see this model. It is called as Dua chart, the Canson model. So this model will tell you how sigma bonding and how pi back bonding are going to happen. So the first step, donation of electrons, remember, from C double bond C. So when I say C double bond C, there will be a reach of electrons there. So we call it pi electrons. This is the highest occupied molecular orbital of your ethene. And those electrons will be given to your empty orbital, to your empty metal hybrid orbital. And secondly, there will be a back donation, as I said previously. So from the filled hybrid metal orbitals to the pi antibonding orbital of your ligand. Pi antibonding of your ligand is actually the lowest unoccupied molecular orbital. Okay? So normally for olefin complexes, they always prefer low oxidation states of metal. For example, we have silver 1, copper 1, and iron 0. Okay, in this case, we have iron with 5 carbonyl. We call it pentacarbonyl iron. So this is definitely 0 oxidation state. And we react with this ligand, cycloocta 1,5-diene. We have 2 double bond here, so that's why it is called diene. I hope you still remember how to name your organic ligand. Okay, so let us count the effective atomic number for iron. So iron is coming from 8 columns, going to be 8 electrons. So we have 3 carbonyl here, so 3 times 2, 6 electrons. So we have 1 COD, cycloocta 1,5-diene. So you're gonna remember this, 1 COD carries 4 electrons. So when you total up, the total electrons would be 18 electrons. Okay. So for ethylene having only 1 double bond, not this one, 2 electron donor ligand like CO. Okay, if you have only 1 double bond, we call it, we're gonna have 2 electron donor ligand. But in polyalkenes, each double bond which binds to the metal center acts as a 2 electron donor. So when you have diene, it's going to have 4 electrons from your olefin, from this diene. Okay. So moving on to the next part of this lecture on hapticity. We have learned denticity, we have learned nuclearity. Now we're going to learn hapticity. Hapticity is actually the number of atoms in the ligand that has a direct coordination to your metal. So we can have many atoms in one ligand, but not all atoms are going to be directly bonded to your metal. So for hapticity is concerned only on the number of atoms from your ligand that is directly coordinated to your metal. So it is actually derived from Greek word haptin, which is to fasten. And then this is the symbol, this is a eta symbol, but it is read as hapto. So for example, I have hapto N nomenclature. So N is the number of atoms bonded to the metal. So it is always indicated by N number. But N is not always fixed. It depends. Because certain ligands will have different way of coordinating themselves to your metal. So for example, we have N3 here. So hapto 3 here. So 3 means we have C3H5. This is the ligand. This ligand is called allyl. So N3 meaning we have trihapto allyl. Now you have eta 5 or hapto 5. This is called pentahapto. Okay, eta 3 we call it trihapto. Eta 5 we call it pentahapto, followed by the name of the ligand. So this is allyl and this is cyclopentadienyl. I have shown you this ligand before, you still remember? So in the structure formula, the totality of pi bonds usually is represented by single line instead of the arrow from each bond. For example, this is N6 hapto 6 C6H6. This is benzene. So it is clearly denoted by one single line. So one single line represents actually the totality of pi bonds. Okay. Now, how do we name pi donor ligands? There are two ways. One, if your ligands are existing as a free state, neutral molecules. For example, C bonded to metal and, for example, olefins such as ethylene or butadiene, arenes, benzene, cyclotetraene. So we use this name as their common name. So we just use olefin, we just use ethylene, butadiene, cyclotetraene, and so on and so forth. But if ligands having odd number carbon with the localized pi system are named as if they were odd electron radicals. Odd electron radicals, for example, C5H5, this is a symbol of radical, or sometimes or simply written as C5H5 negative. This is cyclopentadienyl. So it has both the olefin aim and also radical al functionality. So that's why it is called cyclopentadienyl instead of cyclopentadiene. Yeah? So we have olefin in functionality. We also have al functionality. So therefore, it is named as anyl or enyl. The same with other ligands bonded through an odd number of carbons. Odd number of carbons, C3, C5, and so forth. So C3, for example, we call it allyl. So it's coming from the word propanol, but the common name is allyl. So there are two ways of naming your pi donor ligands. One, if it is neutral, just take it as it is, like olefin, cyclobutadiene, cyclotetraene, and so on and so forth. But if it is odd number of carbon with the localized pi system bonded to your metal, we name it as if they are having some radical functionality. So for example, we have cyclopentadienyl. It does have the olefin part. It does have also the radical part. So it is named as such. Okay. We're going to see more ligands here. So the acting electron rule for pi donor complexes. So we have seen this one table before this showing different type of ligands carrying different number of electrons. So this is about the same concept of table but with different ligands definitely. So you see electrons, pay attention on the electrons contributed and the ligand that we are going to be discussing on. So we have hapto 2 C2H4, meaning there will be two atoms attached to your metal. So hapto 2, this is or dihapto, this is trihapto of your allyl, and this tetrahapto of your butadiene. Okay, you see only two electrons contributed by ethene or ethylene. But for allyl, butadiene, cyclopentadiene, cyclotetraene, they are all going to contribute 4 electrons. Okay, for cyclobutadiene, for cyclopentadienyl, they're going to contribute 6 electrons. So you have to know this because you are going to be given with different type of ligands attaching to your metal. So you have to know when you are asked to find the effective atomic number of your complexes, of your atoms. So you have to know how many electrons contributed by the ligand given in the complex. Okay, let's continue. We have also pentahapto, pentadienyl, 6 electrons, benzene 6 electrons, and we have tropylium 6 electrons, and cyclohepta Triene, 6 electrons. We have cyclotetraene, also 6 electrons. Okay, these are the structure, and please look at the examples that I have attached here. If you have the book of advanced organometallic or something, it is even better. You will be seeing more examples of complexes in the book. I think that's all for today. We are going to learn more in the next video. Thank you very much for your kind attention. Assalamualaikum.